I wanted to, so we're going to talk about those rules for limits, which I wrote at the very end last time. But before we do that, I wanted to do another couple of examples of these showing that the sequence converges, the epsilon business, because I realized after we finished last time, I realized that there was one type of trick which I wanted to go over, but I had forgotten to. So I want to do just one more example, and then I want you guys to try one. And you will see this involves a trick that I didn't do. So slightly fancier trick for doing limits. I want to show that the limit of n squared over, sorry, that's too high up, n squared over n cubed plus 2 is 0. I was going to ask you to say, what's the limit? Remember from calculus, I hope, when the power in the denominator is bigger, then the limit of this type of thing is 0. So what are we going to do? Well, I said this requires a new type of trick that we haven't quite done yet before, but we start off in the same way. So I say let epsilon greater than 0 be given. And then we will find n, a natural number, such that, all right, I do, not that yet, sorry, n greater than or equal to n implies, over here, the absolute value of, it's going to be this thing minus 0, but that's just this thing, n cubed plus 2, less than epsilon, all right? This is what we got to do. Now we begin sort of the work over here. So I'm going to make sort of off to the side, which I don't have enough room to go off to the side anyway, but this thing right here, less than epsilon, we want to try and simplify that. First of all, the absolute values, this thing is already positive, right? Everything inside this fraction is positive, and so we don't really need to consider the absolute values. So it's just going to say n squared over n cubed plus 2 less than epsilon. But the problem really is right here. In this formula here, there's no way to solve for the n because there's 2 of them. You could, if you like, multiply this across, but you'll see that doesn't do any good. You could write n squared less than epsilon times n cubed plus 2. But you're still not going to be able to get n by itself on one side, right? Really, we want to do some stuff and end up saying n greater than some whatever, right? But that is not going to happen given this thing. There's sort of too much business going on there. So there's an extra trick that we can do in such a case, which we haven't. It's not really hard to do, but we just haven't done any examples, so I wanted to do one. We need this to be true, all right? We need n squared over n cubed plus 2 to be less than epsilon. Here's the trick. I'm going to say it is enough if n squared over n cubed is less than epsilon, since n squared over n cubed is actually bigger than n squared over n cubed plus 2, all right? What I did was I just forgot about the plus 2. And that's because this fraction is bigger than that one. So if I want this one to be less than epsilon, it's enough if this one is less than epsilon, this one being bigger than the one that we started with, all right? That's the trick. It's this little, it is enough if trick, okay? You make this thing slightly bigger, but now it's much easier to handle because without the plus 2, actually we can sort of simplify here and get the n by itself. What can we do to simplify? Well, n squared over n cubed is just 1 over n. So I'll continue over here. So we need n squared over n cubed less than epsilon, which is the same as saying 1 over n less than epsilon. And now this is easy to solve. You just say n greater than 1 over epsilon, all right? So this is the trick. When it's too hard to solve for the n, or it's impossible to solve for the n, you can just try to sort of throw away parts of the formula or change some of the formula around to make this thing bigger, right? And then show that this new thing, the bigger thing, is less than epsilon. That automatically means the original thing must be less than epsilon. Let's just see how the proof would finish. I'll write out the third part, the prestige. So we say let the big N is going to equal 1 over epsilon. That's because of this, right? And then I say let the little n be greater or equal to the big N, and we have, I write out all the stuff. So I begin with what we start with, n squared over n cubed plus 2. And then usually we would sort of copy the same steps that we did here, the same simplification steps. But in this case, I'm going to, well, same first thing, which is ignoring the absolute values. And then I'm going to say this is less than n squared over n cubed. So this step where I said it is enough if, and I replace this with that, corresponds to something which is, you know, making the thing bigger, right? It's bigger because I made the denominator smaller. Okay, but then this equals 1 over n, and then now we can do the usual stuff from there. 1 over n is less than or equal to 1 over the big N, and then this is 1 over, not equal, less than 1 over epsilon, which equals epsilon. And that's what we wanted. All right. So this is the trick that I wanted to show. This is actually something we're going to be using quite often, even later on today. This old "it is enough if" kind of thing. All right. Any questions about that one? I got one like this that I want you all to try. So we'll see how it goes. Unfortunately, I can't like walk around the room and see how you're doing. I guess I will just wait, give you some time, and then we'll talk about it. Okay, I would like you to show that this sequence, the sine of n over 2n goes to, anyone want to say? What do you think the answer is here? Sine of n, this is a little weird. Don't worry about it. What do you say?
1 over 2.
1/2?
Yeah.
Any other idea? It's not 1/2.
No, sorry.
You want to think about this fraction when the n gets really big. The denominator will be very, very big, all right? And what about the numerator? Actually, the numerator will not be very big. The sign of n, when you plug in high values for n, it doesn't matter. The sign is always between -1 and 1, right? So what this looks like is a fraction where the denominator is super big and the numerator is like between -1 and 1. What would you say that approach is then?
0.
Yeah, 0 is what we want, because the numerator is never bigger than 1, and the denominator is becoming very, very big. So this is going to go to 0. See if you can do it. And so you should go through the usual steps, but at one point you will realize it's going to be impossible to solve for n. That's because the n is down here, but it's also inside of the sign. So at that point, you want to say something like, it is enough. And then you use the fact that this sign of n in absolute value is always less than 1. This is my hint for where you're going to do this kind of it is enough sort of a trick. All right. So I will give you all a few moments, and then I will, well, I wish I could walk around and see how you're doing. That was not a great breakout room experience, in my opinion. I should have put you like in actual groups, but whatever. Hopefully you know, if you can write the beginning of the proof just as we always do. Once you get down to this point is where you have to have like a real idea for yourself. The first thing you can do is absolute value signs. Perhaps you remember absolute value of a quotient is the same as, so I'm going to say we need this to be true, right? This is the same as absolute value sine n over absolute value 2n less than epsilon. That's just a rule about absolute values, because the absolute value of a product, you can just do absolute value of each part, and same with the quotient. And then once we've split up the absolute value on the bottom, you can just ignore it, because 2n is always positive. So this is the same as absolute value sine of n over 2n less than epsilon. All right. And now is when you can do this sort of, it is enough if I show that whatever, right? Because the absolute value of sine is always less than or equal to 1. That's because sine of x is always less than or equal to 1. So I'm going to say enough to show that 1 over 2n is less than epsilon. And then this is now easy to solve for n, all right? It's just going to be, i.e., n is greater than 1 over 2 epsilon, right? And then we go through the end of the proof. So this is how we choose the big N. Let's see if I can write out the rest of the proof then. So I say let the big N equal 1 over 2 epsilon, and let little n be greater or equal to the big N. Then what do we got? We have sine, so I begin with absolute value sine n over 2n. And then I say this equals absolute value sine n on top over absolute value 2n, but absolute value 2n is the same as 2n. And on top, absolute value sine n is less than or equal to 1. All right. This is the trick. This is where it all pays off. And then this 1 over 2n is basically the same as epsilon. So here I'll say less than or equal to 1 over 2 big N, and then that equals 1 over, not equal, less than 1 over 2 times 1 over 2 epsilon, and that equals epsilon. So that's how we do that. All right, I hope you got something like that. There were mixed results in the breakout rooms, I would say. Anybody have any questions about that? I hope that it makes sense, at least when I do it. You will have a chance to practice some of these on the homeworks. All right. All right, that's all I wanted to do for those. I just wanted to do those 2 more examples of doing the limit with this extra little kind of trick in the middle. Today, our major topic for the second half, I guess, is going to be these rules for limits, which I wrote down last time. Rules for limits. I'm going to switch markers here. I got new markers. Got to shake them. Shake them. All right. Rules for limits. They are things like, so here's what the theorem says. We're going to talk, well, we'll prove like parts of it. It says let some sequence AN approaches A and some other sequence BN approaches B, then, and some constant C, a real number. Then the following things are true. The limit of CAN is equal to CA. That is, if you just multiply the sequence by a constant, then the answer is that same constant times the limit. In other words, this another way of saying this is you can factor the C out of the limit, and you get C times the limit of AN. The second thing is about adding the sequences together. Limit of AN plus BN is A plus B. That is the limit of the AN plus the limit of the BN. Another thing is about multiplying the limits, or multiplying the sequences together. The limit of AN BN is equal to A times B. And then the last one is about a quotient, AN over BN. And what you get is A over B, provided that B is not 0. If B is 0, then it's not clear what happens here. If B is 0, actually you can't say anything. Sometimes it'll sometimes the limit will be 0, sometimes there's no limit, sometimes it equals something else. All right, these are the rules. These are rules that you should have learned in a calculus class at some point, and you use these rules all the time when you're doing limits in calculus. Let's see if we can demonstrate the first one. So I'm gonna write just the first one again. This is what we need to show. So I'm gonna say let the limit, or an approaches a, and some constant, c, a real number. And then we'll show can approaches ca. All right. Okay. Now I'm going to write this, it's going to be a proof, but actually we will follow, for the most part, the same old structure as showing the limit of some sequence equals something, because that is in fact what we have to show in this case. We have to show the limit of this sequence equals that number. All right. So for my proof, I'm going to do it in the same way that I always show that the limit of a sequence is something or other. I'm going to say let epsilon greater than 0 be given. And we must show, or we must find some big N, a natural number. You know how this goes, right? Such that N greater or equal to big N implies. Okay, what do I write here? Can anyone say what should go here? It's something or other less than epsilon, right? Somebody shout it out. Anybody shouting?
Would it be CAN?
Mm-hmm. That can-do spirit. That's not all of it.
CAN minus CA.
Yeah, CAN minus CA. Thanks. Remember, in here, what you always see is, usually it's AN minus whatever the limit is that we're trying to show is the limit. In this case, our sequence is CAN, and we're showing that the limit is CA. So here's the sequence term. Here's the value of the limit. Excellent. All right. Now we, as usual, will try to do some business here to simplify if we can. So let's say what I'm about to write is kind of a little sidebar, as usual. I don't have enough space to really put it off to the side, but let's see if we can do anything to simplify here. Any ideas? Can we do anything to simplify that? There is one thing that I think you can do. What do you think?
Can we take out a C from both?
Yeah, take out the C here. So you can factor C and write it this way. C times AN minus A, right? Those are the same. And then we can use a rule of the absolute value. Here I have the absolute value of two things multiplied together. That's the same as multiplying the two absolute values. So this is absolute value C times absolute value AN minus A, less than epsilon. Now, we're not going to be able to solve for N here, of course. Like in an ordinary one where you have a specific sequence in mind, you try to solve this for N. That's not possible here because we just have this. But I can solve for this, AN minus A, by dividing the C. It says AN minus A less than epsilon over absolute value of C, all right? And remember, all of this is with the prefix of, we need AN minus A in absolute value to be less than epsilon over absolute value of C, all right? And now this is something which can be true because AN converges to A. That means that AN minus A can actually be less than epsilon for any epsilon. So this is something that we haven't really done before in one of these proofs, but we are going to use the fact that AN converges to A, all right? Since AN converges to A, this AN minus A eventually becomes smaller than any number, right? Smaller than any epsilon. In particular, we can make it smaller than epsilon over absolute value of C. So what we're going to do is, I'm going to say, can you still see down here? I'm going to start again at the top, just so I don't run out of space at the bottom. Since AN converges to A, we can find some big N, a natural number, so large that AN minus A is less than epsilon over absolute value C, all right? This is because the definition of what it means, what it means for AN to converge to A, it means for any epsilon, we can make this less than epsilon. So in particular, I can make it less than epsilon over absolute value of C, all right? Can I say, by the way, I'm assuming that C is not 0. Sorry, I probably should have mentioned this before. If C is 0, then the whole thing is obvious. You just get 0 for the limit immediately because everything here is 0. So we're assuming C is not 0. If C is 0, you can't do all of these same tricks, but the whole theorem is much easier if C is 0 anyway. Okay, we can find some natural number so large that an minus a is less than epsilon over C. So this is because we, if you like, we are using the definition of an approaches a, but with, instead of just using it with epsilon, we are using it with epsilon over C. And that means that there is some n such that an minus a is less than epsilon over C. So with epsilon over absolute value C in place of epsilon. But we can do that because the definition of this says something is true for any epsilon. So we can use whatever epsilon we want, all right? When we are using the definition of a sequence having a limit, we can use whatever epsilon we want. That's the moral of this little story here. All right, we can find n so large that this is less than epsilon over C. Okay, and now we have chosen the n, and we complete the proof in the way that we always do. So now I'm going to say, now let little n be greater or equal to big N, and then we have, and I begin with the thing that I'm trying to show is less than epsilon, is that CAN minus CA. And now I want to do blah, 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 eventually saying something being less than epsilon over here. What should I do first? Just like in our normal proofs, you want to try and mimic the same steps that you used on the sidebar. What do you say first? I'll have a sip of my beverage. What do you think?
Taking out C as a common.
Say it again, I didn't hear that.
Taking out C as a common.
Yeah, factor out the C as a common factor. C an minus a, right? And then we can split the absolute values like we did. Absolute value C, absolute value an minus a. Okay, now what? What do you think? You can't really do much with the C. What can I do with an minus a? We actually did say something about an minus a. Perhaps something still visible?
C. Replace it.
Somebody want to shout it out? The C I'm going to leave like it is. What can I do with an minus a?
Epsilon naught over C.
Yeah, we said up here, the choice of the big N makes it so that an minus a is less than epsilon over C. So this, I leave the C the same, but this, I write epsilon over absolute value of C. And now this equals epsilon. And that's it, right? This, so absolute value CAN minus CA less than epsilon, which is what we wanted. All right. That's how we do it. Very similar structure to this proof as the other one, although it's a little weird because we're using this, we use the fact that the other sequence converges to show that this has to be less than something or other. All right. Any thoughts about that one? I wish we could all be together. I feel like it's a little easier for me to tell how everybody's doing if I can see at least your eyes, although not your nose and mouth. All right, let's talk about the second one. This was about multiplying a sequence by a constant, where we used this kind of a trick. Let's try the second one, which is about adding two sequences together. So the second one was, I'm going to say let an converge to A and Bn converge to B. And then we'll show that an plus bn converges to a plus b, right? This one is going to use a different kind of trick, which is another trick that we're going to be using fairly often when we're doing these kinds of epsilon tricks. I'm going to say, I'll just tell you right now, use the epsilon over 2 trick. The epsilon over 2 trick is a thing that you use often when you're talking about adding 2 things together, and you'll see what I mean once we get there. Anyway, we are going to begin the proof in the usual way. Because I'm trying to prove that this thing converges to a plus b, we have to structure it in the same way that we always structure our epsilon proofs about something converging to something or other. So I'm going to say, let epsilon greater than 0 be given. Then we'll find n, a natural number, such that n greater or equal to n implies absolute value an plus bn. So this time you take the sequence term minus the limit. So it's going to say an plus bn minus a plus b. Like that, less than epsilon. Right on the edge there. All right. And now I'm going to do my sort of work on the side here. We have this thing. What can we do to simplify that? Well, an plus bn minus parentheses a plus b. This is the same as, you can't do a whole lot with this, but at least can we write the a's next to each other and the b's next to each other? This is an minus a plus bn minus b, all right? And I want this to be less than epsilon each time. Okay, we're gonna do like in the examples at the beginning of class today. I'm gonna do one of these like it is enough to show that whatever. So here I have absolute value of 2 things added together. Now, this is not equal to the absolute value of each one. Remember, if I have something like absolute value x plus y, this is not true, but this is true, right? This we talked about maybe on the first day of class, second day. This is the triangle inequality. It says if you have the absolute value of 2 things added together, it's less than or equal to each of the 2 things separately. And that's what we're going to use here with the old it is enough reasoning. So we need this thing to be less than epsilon. I'm going to say it is enough, E-N-O spelling, enough if this is less than epsilon, right? I did the triangle inequality. See this, I need to make this less than epsilon, but this thing is even bigger. So it would be good enough if we were able to make this thing less than epsilon, all right? And why did I want that thing? Well, here comes the epsilon over 2 trick. I will continue up here. If you need to make 2 things added together being less than epsilon, I'm going to say, again, it is enough if an minus a less than epsilon over 2 and bn minus b less than epsilon over 2. This is the epsilon over 2 trick. If you have 2 things added together, you need to make them less than epsilon. It is good enough if you make each one less than epsilon over 2, right? Then when you add them together, the result will be less than epsilon. So that's what we call the epsilon over 2 trick. We will use it often. All right. And then how do we do this? Now this is like the previous example. Remember, we have already assumed that an minus a, or that an converges to a, which means we can indeed make an minus a as small as we want. So we can make it less than epsilon over 2. And similarly, we've already assumed that bn converges to b. And so we can also make this one as small as we want. We can make it less than epsilon over 2. So I'm going to say, since an converges to a, and bn converges to b, we can choose n so big that when n greater than or equal to the big N, we have absolute value an minus a less than epsilon over 2, and absolute value bn minus b less than epsilon over 2. I hope that all fits on the screen there, right? Because an converges to a and bn converges to b, that means that we can make these as small as we like. In particular, there's some n which is so big that when n is greater, that means that each of these will be less than epsilon over 2. And this is the choice of n that is required to make the end of the proof work properly. All right. Let's write out the rest of the proof. So then, when n is greater than the big N, we begin with, remember what we started with originally, we had to show was less than epsilon. It was an plus bn minus a plus b, like that. Okay, this is equal to an minus a plus bn minus b. And this, you do the triangle inequality, less than or equal to an minus a plus bn minus b. And then these guys are each less than epsilon over 2 because of our choice of the big N. We chose the big N big enough so that each of these are less than epsilon over 2. So these are less than epsilon over 2 plus epsilon over 2, which is epsilon, which is what we wanted. All right. This is how we show the second of those, that the limit of the sum is the same as the limit, the sums of the limits, all right? Any thoughts about that one? What are your questions about this one? Ain't nobody got any questions. All right. I wanted to do the third one. We've only got 5 minutes left. Maybe we can just get the third one going a little bit. The third one is not really a different kind of trick. It's kind of a combination of what we had done in the previous ones. For the third one, maybe, how about we'll write the proof in detail next time. Let's just talk about the basic idea. The third one, you need to show that an bn converges to ab, right? So when it comes time to actually writing the sort of the work on the side, let's see if we can make that happen. This would be absolute value an bn minus ab less than epsilon. This is what you have to, get to. The problem here is it's not possible to split out an minus a and bn minus b the way that we did in the previous example. Because of the way this multiplication is written out here, they're kind of permanently stuck together. And so this is, you have to do a trick here, which is kind of a special purpose trick that you wouldn't really have a reason to think this up. But once somebody brings it to your attention, you will realize that it's a good idea. We are going to replace this by an, so this is the same as, check it out, an, bn, this is the old subtract and add the same thing. And I'm going to add and subtract abn. So I go an, bn minus abn and then plus abn minus ab, that's from above, all right? And then this thing, so the trick here is now we can break it into two parts, each of which can factor something out of it. So the first part, I'm gonna say, according to, by the triangle inequality, I'm gonna break this absolute value part. Absolute value of two things added together is less than or equal to each of those two things in absolute value. So an bn minus abn plus, and then here abn minus ab, like that. And now we can factor parts out. This actually is equal at this point to, here I can factor bn, an minus a, plus here I can factor a, bn minus b. And now we can make this guy super small and this guy super small with some kind of epsilon over 2 kind of action. Although you will see it's not exactly the epsilon over 2 sort of a thing. But this is the idea of that proof. Maybe we will leave it at that and we'll start off at the beginning next time doing the real details of this. All right. Any thoughts about any of that? I know this is kind of tricky little stuff, but I think we can handle it. All right, I think that'll do it for today then. I will see you all tomorrow. Homework is due tomorrow. I hope you've had a chance to check it out.